Hello everyone. Today we're taking an in-depth look at preemptive shortest job first, more commonly known as shortest remaining time first or SRTF. It is a fundamental CPU scheduling algorithm in operating systems. Our goals are to comprehensively define SRTF, understand its preemption logic, apply it in an example, analyze its performance and challenges like starvation, and finally compare it to other scheduling methods. Before we dive into SRTF, let's quickly remember why CPU scheduling is so vital. It is about efficiently managing our most critical resource, the CPU. Good scheduling makes our systems responsive, ensures fairness, and aims to optimize key performance metrics like throughput, turnaround time, and waiting time. The core idea behind SRTF is simple: always prioritize the shortest task. Think of an express checkout. If a cashier can briefly pause a long transaction to quickly process someone with a single item, everyone on average waits less. SRTF applies this to processes. It is the preemptive version of shortest job first, meaning the CPU is always given to the process closest to finishing its current burst, and it can interrupt a running process if a new, shorter job arrives. It constantly reevaluates the shortest path.
The heart of SRTF lies in its preemption mechanism. Preemption isn't random, it's calculated decision. It primarily occurs when a brand new process enters the system. The scheduler then immediately compares the newcomer's total burst time with the remaining time of the currently running process. If the new process is shorter, the current one is paused, and the new one takes over. This relentless pursuit of the shortest job is what drives SRTF's efficiency. This flowchart illustrates the SRTF algorithm's continuous decision-making process. The scheduler is always vigilant. When the CPU becomes free or a new process arrives, it checks all the available processes. It then compares the shortest remaining time among all the ready processes with that of the current running one. If a shorter job exists, preemption occurs, ensuring the CPU is always working on the most efficient task.
Now for a first example, we have four processes P1, P2, P3 and P4. Observe their arrival times and their total burst times. These varying arrival times are crucial because they will trigger the preemption logic we just discussed. As we proceed, always keep in mind the remaining burst time of each process as that what SRTF cares about. Let us meticulously trace the execution. At time 0, P1 begins. At time P1, P2 arrives. Its burst is 4, shorter than P1's remaining 7, so P1 is preempted. At time 2, P3 arrives. Its burst of 1 is even shorter than P2's remaining 3, so P2 is preempted. P3 runs to completion at time 3. Immediately, P4 arrives, and its burst of 2 is shorter than both P1's and P2's remaining times, so P4 starts. Now continuing our trace, at time 5, P4 finishes. Now comparing P1's remaining 7 with P2's remaining 3, P2 is shorter, so it takes over. At time 8, P2 finally completes. With only P1 left, it gets the CPU and run until it finishes at time 15. The Gantt chart clearly visualizes this entire sequence of execution and numerous preemptions. Now that we have the schedule, we can calculate the performance. Turnaround time measures the total duration a process spends in the system from arrival to completion. Waiting time is accumulated time a process spends in a ready queue, waiting for the CPU. Notice how shorter the jobs P3 and P4 benefited greatly, achieving zero waiting time. Our average waiting time of 2.5 milliseconds demonstrates SRTF's efficiency in this scenario. SRTF offers significant advantages. Its optimality in minimizing average waiting time is a major highlight, translating to high throughput and responsiveness, which is great for user experience. However, it comes with serious drawbacks. The risk of starvation for long jobs is a big concern. The constant context switching creates performance overhead, and most critically, it assumes we all know the future exact burst time, which in real world operating systems is only an estimation. Let's tackle the issue of starvation, which is when a process never gets to run because other higher priority or shorter jobs always arrive. A common solution is aging. This technique gradually increases a process's effective priority or decreases its perceived remaining time as it waits in the ready queue. Over time, even a very long job will eventually become short enough or high priority enough to finally get the CPU, thus breaking the starvation cycle. This makes SRTF more practical in real systems.
This table provides a snapshot of SRTF against other popular scheduling algorithms. You can see SRTF's strength in average waiting time optimality, but also its weakness regarding starvation and also reliance on future knowledge. Non-preemptive SJF shares the future knowledge problem but has less overhead. Round robin offers fairness and more starvation but isn't optimal for throughput. FCFS is simple but generally performs poorly on average metrics. Each algorithm has its own niche. So, to bring it all together, shortest remaining time first is the relentless pursuit of efficiency. It's the algorithm that, in a perfect world, would make our CPUs the most productive they could ever possibly be, minimizing waiting time and making systems feel incredibly responsive. But as we have seen, this pursuit of perfection comes at a cost. In its pure form, SRTF can be brutal meritocracy, where only the shortest jobs thrive, leaving longer processes in a dark and classic case of starvation. It operates on a crystal ball of future knowledge that we don't actually possess, and its constant context switching creates a noisy overhead. This is the beautiful fundamental trade off at the heart of operating system design. We are always balancing raw performance against fairness, predictability, and practical reality. SRTF isn't just an algorithm, it's a philosophical benchmark. It shows us the absolute limit of what's possible for minimizing wait times. While we may never use it in the pure theoretical form, its principles inspire the smart, adaptive schedulers in today's operating system that use techniques like aging to inject fairness into the drive of efficiency. It teaches us that the goal isn't just to be fast, but to be smart and fair. Now let's test the understanding with a quick quiz. Which metric does SRTF primarily aim to minimize? Average waiting time. What is the challenge SRTF faces regarding long processes? Starvation. The future knowledge problem refers to the need for what? Estimating process CPU burst time. Thank you. Now understand not just how SRTF works, but why it matters in the grand conversation of system design. Final takeaway: SRTF represents the ideal of maximum CPU efficiency. It provides a gold standard benchmark for minimum average waiting time, demonstrating the power of prioritizing short tasks. However, its real world value lies in the lesson it teaches about system trade offs, the tension between performance and fairness, and the engineering integrity required to approximate its benefits. Example, through aging and burst time estimation while mitigating its critical flaws of starvation and overhead. Understanding SRTF is to understand the fundamental goals and challenges of CPU scheduling.